Hi, for this second video, I'm going to be talking about quantum walks and the underzone localization problem. So for the quantum walk, we suppose we have a system, and that system could be in the states x1, x2, x3, up to the state xn. So we can draw, let's say, for example, for 5 possible states, we can draw some nodes, and then if there's an allowed transition between 2 states, we connect them, and in that way we can form a graph. So in this case of 5 possible states, we can make a transition between the state 1, state 2, state 1, state 3, and state 1 and 4, 2 and 3, and 3 and 5, 4 and 5. And each transition will have a probability which could be discrete or continuous depending on the nature of the problem. So in the quantum case, the evolution is given by the time evolution operator, which is of this form, and we can compute the state at any time using this expression here. So the state 0 could be any will have any probability distribution, and then as time passes, as the system evolves with the Hamiltonian that's given by the possible transitions between the states, it will determine what the probability distribution would be at some time t. So for example, the probability of measuring the state xn is given by this expression, and that's in general the probability distribution we will have. So we can imagine the problem this way. So let's say we have again 5 possible states or 5 sites, and there's a transition probability between each of the states. In this case, we have a one-dimensional lattice, and the particle will be hopping. In fact, in the code, we'll be simulating this walk by the tight-binding Hamiltonian we saw in the previous video. And there's a transition probability called gamma. And so for any state or any site n, we'll have the following relation. So we can define some Hamiltonian. We can build it by assuming how the probability transitions are. So, for example, if we take n as a reference, we can get out from the state n to the left, so get to the state n minus 1 with a transition probability gamma, and we can also get to the state to the right side, so it's also gamma, and as it's going out, we have a minus sign, and we have 2 ways in which the system can get to the state n, if it goes from the left or if it goes from the right. So we have to account for those 2 cases, and we can define this Hamiltonian in that way. So from this relation, we can compute this expression. We just need to write it as a power series of this h. So this is minus it to the m equals 0 to infinity over m factorial, and this is h to the m. And we know h, how it's applied on n, so we can find relations. We can find an expression for x to the mth power, and that's all we need to compute the state at some time t, and it's given by this expression. I'm not going to give the proof here, but I'm going to drop some links in the description. So The thing is that after writing this Taylor series and finding an expression to this, we can use a relation, an expression for the Bessel functions. Actually, the first kind, Bessel function. And here we have the function, and we also have a phase, which is some function which is different for each index n, and depends on the transition, probabilities, and time. But that's not actually very important for what we need, because the probability of state n is given by this. So the phases vanish when we take the absolute value, and we only need to compute this. So that's all we need to find the probability distribution of the system after some time t. And we'll see when in the code section how the probabilities are different for the classical case and for the quantum case. And there's a very interesting point due to the variance or the standard deviation of these distributions that has some applications on search algorithms. Now for the Anderson localization problem, we only need to add some extra terms to the tie-binding model. So we saw that tie-binding model has the hopping between sides. In the case of one dimension, it's just hopping between, we can restrict to nearest neighbors left and right. And so this is the term we saw before. But now we can add some inside energies to this model. So for the tie binding case, the only tie binding, we have that all sides have the same energy. So a side to be occupied requires some energy from the system. And for the previous case, we can set it to 0. So inside energy is equal to 0. Which is actually some reference, but we can add some randomness to these levels. So to be at side 1, we require some energy, let's say epsilon 1. To occupy the second side, we require some other energy. So there are energy differences between two sides. So the system has to have some energy to hop between two sides. So that's what this term is telling us. And we can make a drawing. So this is the first side, second, and we can draw them at different heights, so we remember, so we have in mind that each side requires different energies. So for hopping, it has to go uphill, in sort of saying, and that's the problem. So that's called the Anderson model, and we can write these energies in some other way. So we have another model, and that's what we're going to see in the code. We're going to make a restriction for these epsilons, and that's going to give us some structure, and we can analyze the evolution as well. So we're going to restrict to one particle case. So we have, in this case, I also drew 5 sides, and we're going to put one particle in one of those sites. So one of them is going to be occupied. And then we're going to make the evolution according to this Hamiltonian, and we're going to track the probabilities of the particle being at each site. And we can write a general wave function of one particle as this. So here n is the site index. So we have it is the creation of one particle at the site n, and here's the probability or the coefficient associated to the creation, to the particle being on that site. So given this general form of the one particle wave function, we can propagate the Hamiltonian. We can just solve the time-independent Schrodinger's equation, which is this. So after applying the Hamiltonian on the wave function, we can find the following relation, which is a recursion relation between the coefficients, so between the probabilities of the particle being at different sites. Now we can write this expression, which has here is the term associated to the site energies, and here's just in the right hand side we have the energy of the system, and here is the probabilities or the coefficients of the neighboring sites. So we can write this relation in this way. So to find the n+1 coefficient, we need the two previous coefficients, and we can use some theorem, which I'm going to drop in the description as well, but it's a bit complicated. But the thing is that it can be shown that this relation leads to an exponential decay. Let's write as n. So here is this is actually the relation. So n is proportional to this exponential, which is negative, and this is for n to infinity, or big N, we have this exponential decay, and that happens only when this epsilon comes from some random set of values. So it has to be some randomness in the system. We require it for the theorem to prove this, to satisfy this relation. And the main result about this, the main interpretation, is that if we start from some site, so the wave function is localized, then for a very large n, so here's the n, a big n, here the probability of having the particle far away from the initial condition is very close to zero, which means that the probability distribution is going to be localized in some region of space, and that's called the Anderson localization. And we're going to simulate it using this Hamiltonian, so we only need to add the inside energies, which are going to be random, and of course we need to write it in the qubit space to simulate it on the quantum computer, and that's what we're going to do in the next section.